Okay, can everyone see my screen now? Great. Okay, thank you. Okay, so thank you very much for the kind invitation. It's a pleasure to be here. What is, I guess, this afternoon in the UK and is this morning here on the West Coast. So I'm delighted to be able to talk here. So as was said in the introduction, my background is numerical analysis. So I think I'm going to bring a slightly different perspective to the sort of talks this morning, because I'm going to talk about the use of deep learning in scientific computing problems. So this is something that has been receiving a lot of attention in the last 3 to 4 years. If you go to the large scientific computing conferences, there's now a large amount of machine learning and specifically deep learning being discussed at these events. And so what I want to discuss is I want to sort of give two stories discussing the sort of gap between the theory of deep learning and its practice in scientific computing. And this is based on the type of research that I've been doing over the last, I guess, 5 to 10 years. So let me start by acknowledging my collaborators. So this is combining together a lot of joint work with a lot of different people. So I'm fortunate at SFU to have a great group of students to work with, including my postdoc, Nick Dexter, who's been very heavily involved in this, a string of my PhD students, and let me also highlight Max Nestorenko, who's a master's student, who's also, I'll be discussing his work towards the end of the talk. At Concordia, my former postdoc, Simone Brigier-Pallier, has been very involved in this. Then I've worked extensively with a group of people at Cambridge, including Anders, one of the organizers here, a couple of his PhD students, including Nina Gottschling, Vegard Anton, who's at University of Oslo, and then finally another collaborator of mine, Clayton Webster, who's at UT Austin. So okay, so let's get started. So deep learning, if you interact at all with the scientific computing community, you will know that deep learning is being actively applied to scientific computing problems. So what do I mean by that? I mean, perhaps most prominently, numerical PDEs, so numerical methods for solving partial differential equations, discovering dynamics of dynamical systems, so trying to infer physical laws from experiments, parametric modeling and its applications in uncertainty quantification, which I'll talk about next, and also inverse problems, in particular inverse problems arising in imaging. And there are various other applications as well, which I won't touch on. So perhaps the first question to ask is, why use deep neural networks for scientific computing problems? Of course, one answer to this is, well, because there's been a deep learning revolution in the machine learning community where, as we all know, it's achieved outstanding successes. So why not try it for scientific computing problems? So that's one argument. But the argument that I'd like to focus on, which is often an argument used on the sort of more numerical analysis or the more sort of mathematical side, is the following. And that is that there's a rich literature on what I'll call DNN existence theory. So deep neural networks are extremely expressible, and there's a growing, a very rapidly growing literature describing their approximation theoretic properties for wide classes of functions, okay? Whether they be functions in Sobolev spaces, so HK functions, analytic functions or holomorphic functions, piecewise smooth functions, band limited functions, Baron functions, cartoon-like functions, etc., etc. It's actually, this community is so active now, it's very hard to keep pace with the latest results that are being proved here. If you're interested in this, I won't review this at all. There are now some excellent review articles that have come out in the last year or two. So this is an answer that's often used to motivate the use of deep learning for scientific computing. But it's important to emphasize that these results are existent theorems. They say there exists a deep neural network of a given architecture that achieves some approximation bound. They say very little about the practical performance of deep learning. What I mean by this is, in terms of what we consider in numerical analysis, the sort of key pillars of how we understand algorithms. So first of all, stability. So the robustness of an algorithm to errors, whether these be floating point errors in the computation or noise in measurements or something like that. Accuracy. So how does the error behave as a function of whatever parameters you have? So the size or the architecture or the number of samples or whatever. Sample complexity. So how much data do you need for the problem? If you're trying to solve a PDE, how many samples do you have to take? And computational cost. You know, how much does it take to run the algorithm? So really, this talk is going to try and highlight through two different application areas the ways in which existing deep learning approaches don't kind of meet all these criteria, or the ways in which they fall short of these criteria. So the sort of general question that I want to pose, and that I'm not going to attempt to answer, but I'm going to try and give some insight into, is how effective is deep learning as a tool for scientific computing problems? And in particular, are there ways of training deep neural networks for a given problem that provably match or outperform the state-of-the-art techniques for those problems? So here's a summary of the talk. The talk's going to be in two parts that are topic-wise are not connected, but hopefully the theme is going to be consistent throughout them. So in the first part of the talk, I'm going to talk about deep learning for parametric model problems. So this has applications in particular in surrogate model construction in UQ, and also more generally in parametric PDEs. And the bad news here is that despite there being some very strong existence results for these types of problems, what we'll see is that deep learning can perform quite badly and quite unexpectedly on even pretty benign function approximation tasks. So really at its heart, this is a function approximation problem, and we'll see that deep learning can offer some quite subpar performance. So that's the bad news. Then the good news, which is a theoretical result, is to show that there are provably good ways of performing training for these problems. There are deep neural network training procedures that can perform at least as well as the current state-of-the-art methods for these types of problems. So that's the first part of the talk. And then the second part of the talk, I'm going to shift gears and talk about inverse problems, and specifically inverse problems in imaging. So this has all sorts of applications in medical, scientific, and industrial imaging. And the first thing that I'm going to show here, and I think this has already been highlighted in earlier talks this morning, for example, by Des Hyam, and maybe also by Janina, is that existing approaches for image reconstruction are susceptible to instabilities and hallucinations and generally unpredictable generalization performance. So that's the bad news. I'll show a number of examples of that. We'll get into the theory of why this can occur. But then on the good news is that we'll show that there are efficient deep neural networks that can perform at least as well as state-of-the-art sparse regularization methods for these problems. Okay, so that's the outline of the talk. Let's get started with the first part. So I'm going to talk about deep learning for parametric model problems. So first of all, let me give you one slide to sort of introduce the general problem. So this is a pretty broad problem. But the idea of parametric modeling is to understand how the parameters in a physical system affect the output. So think of a weather or a climate model, or a chemical or a biological process, or many, many other systems. All these types of physical systems involve parameters. If you want to study your system, you have to set these parameter values. And oftentimes we're interested in how our output depends on the parameters that we set. So in a weather or climate model, we're interested in is the temperature going to go up or is it going to go down, depending on the parameters that we feed into the model. So mathematically, we can just think of this as a problem where we have an input y, which is a vector of parameters. We have some black box f, which is our model, and it spits out an output f of y. Yeah. So oftentimes this black box is a solution of a PDE or a system of PDEs, because often in practice, we model a physical system with a system of PDEs. Generally, what we think of is that we have some large-scale computational code that is performing this black box. So we have some well-tuned and highly adapted PDE solver that solves our system of PDEs. Okay? So we think of this as a black box. However, evaluating this black box is often pretty expensive. Okay? So it involves solving a numerical PDE or perhaps performing physical experiments depending on the problem. So the whole idea of what's called surrogate model construction is to try to approximate this black box. Okay? The idea is directly working with this black box is expensive, so let's construct a cheap approximation to our black box that we can then work with. And so the way in which we think about doing this is to construct it from the approximation from sample values, or otherwise known as snapshots. Okay? So these are just evaluations of our black box at a set of parameter values. Okay? Why do you want to do this? Well, typically, often what you want to do is you want to perform some kind of downstream task. So you might want to do uncertainty quantification, so understanding the statistics of your output, if you think of your input as stochastic, or you want to perform parameter optimization. So find the value of y that maximizes or minimizes this function. Or maybe you want to solve inverse parametric problems. So find the value of y that corresponds to a given output. All of these tasks are very difficult if you work with the original black box. They become easier if you first approximate it with a surrogate model. Okay, so that's the parametric modeling problem. And the first thing to highlight is this is generally a challenging problem. Right? There are at least 4 things that make this problem inherently difficult. So first of all, the dimension is high. Okay, so any kind of sophisticated model involves a lot of parameters. So I'm talking on the order of tens or hundreds or potentially even more. Secondly, generating data is expensive. Okay, every time I have to probe my black box, I have to solve a numerical PDE, or I have to, say, perform physical experiments depending on the setup. So I'm limited in the amount of data I can acquire. There's also error in the data, so noise in physical experiments, modeling errors, discretization errors, et cetera, et cetera. And finally, my model might not be scalar valued. Okay, so my model might actually output a function, depending on what I'm interested in doing. So I see one answer in the Q&A. So I'll try and answer these as I go along. So from Colin Roat, naive question regarding surrogate models. Are orthogonal bases, e.g. Chebyshev, helpful? Yes. So actually the sort of state-of-the-art methods that I'll talk about are based on orthogonal polynomials. Okay, so the idea of sort of using deep learning to solve parametric or to perform surrogate construction is pretty straightforward. It's to view the data that you get as training data and then just train a deep neural network approximation to your underlying function. Okay, so surrogate modeling and surrogate model construction is a big area of scientific computing. And so when Nick arrived as a postdoc a number of years ago, I said, let's try and understand how well deep learning can work for this problem. And let's strip the problem down to its essence, and let's just think about function approximation with deep learning with a particular focus on understanding how much data, how many samples we need of our function to get some sort of guaranteed accuracy. So Nick has this framework, a package for doing these kind of experiments, and it's basically just allows you to test different deep learning approaches, but it also allows comparisons against polynomial-based methods, which are some of the state-of-the-art methods for these types of problems. So we started with extremely simple problems. Okay, we started with a simple one-dimensional function approximation problem, and I think anyone who's really tried to do this will know that actually getting this to work involves a substantial amount of effort. It's not a naive issue of just setting up some model, clicking run, and getting good results. Okay. And the first thing you discover is that there's a very delicate balance between your architecture size and your accuracy. So here, this is a bunch of experiments. What we're doing here is we're comparing the error versus the number of samples, okay, because that's the That's the focal point for this type of work. And so the solid lines here are polynomial-based methods. Don't worry about what the two lines correspond to. That's not really important for this talk. And the dashed line here are different types of deep neural network approximations. And what you see is, okay, there's a careful balance to try and get competitive accuracy here versus the number of samples. So this is a simple example, and already in this simple example, you see the sort of one of the key challenges, which is setting your architecture size. And just a little bit more emphasis here, here's training on another simple one-dimensional function. And you can see that the narrower, shorter architectures don't give a good accuracy. Wider architectures end up with various spikes and things like that, even though this is a nice, simple, smooth function to train on. Once you go to higher dimensions, things sort of get more interesting and sort of more surprising in many senses. So here are two functions in 8 dimensions, still not a very high dimensional problem. And what you see in the first function, this is an extremely smooth function. This is not a difficult function to approximate, as you can see with the polynomial-based methods do extremely well here. All the deep neural network methods struggle. And this is despite the fact that the existence theory, as I'll discuss a little bit later, says that there's a deep neural network that should achieve this type of error. So what you're seeing here is that you're just not training a good neural network. Okay? And this, I should say, emphasize here, all the training here is done with standard methods, standard architectures. There's nothing particularly fancy going on. On the other hand, on this more complicated function, again, now you start to see competitive performance. You can play around and also change the architecture as well. So here I'm just changing the ratio, the depth and the width of the neural network. Okay, so then we were sort of rather disappointed by this kind of performance. Then we started to look at just sort of piecewise smooth function approximation, even though, and this is a kind of sort of model for something that does occur in parametric modeling. You can have sharp transitions with respect to your parameters for various models. So it's interesting to look at these kind of piecewise problems. Here, you would definitely not want to use a polynomial method. And so at least the sort of deep learning works here and gives you an approximation error that's sort of decreasing. However, there's a pretty substantial artifacts or pretty substantial effect that one sees in the case of dimensionality. So even when the dimension is 4, so pretty low dimensional problem, you start to see substantially worse result than when dimension is 1 or 2. Okay, so there's a lot more in our paper, and I won't get into any of the technical details about that. If you're interested, please go and take a look at the paper. The sort of main takeaway here is that there's a gap between the approximation theory of deep neural networks. So the existence theory says that for all these problems, there's a deep neural network that can achieve a small error. But what we're seeing is that there's a gap between this existence theory and the practical performance. So when we have a limited number of samples, which is the sort of key issue in this this type of problem, we are not able to train and get that good network. So Nick spent a lot of time doing this work, and we were sort of quite disappointed with the conclusions that the results that we were getting from this. And then we sort of thought, well, what can we do next? Can we try and establish, at least theoretically, that there are good ways of doing things? So we looked for some theoretical insights. And while we were sort of preparing ours, Philip Gross and Felix Voigtlander also wrote some nice work on this. And they essentially showed some upper bounds on performance. So they showed that there are classes of functions that are well approximated by deep neural networks, so for which you have existence theorems. However, they necessarily require a lot of training data to train those functions. Okay? So this is a negative result. This says that there are problems that you might encounter where the amount of training data that you need is going to be exceedingly large, more than you're likely to have available in practice. So what we instead tried to look at was the idea of lower bounds. Can we show that there are ways of training deep neural networks for these types of problems that perform at least as well as polynomial-based methods? So in order to understand this, we need to, at some point, declare a class of problems that we're going to work on. And there's a natural class of problems for this type of application. And that's to look at functions that are smooth, okay, and more precisely functions that are holomorphic. The problem class we're going to consider is functions f mapping unit or symmetric hypercube of side length 2 in d dimensions. And we're going to allow the functions to be Hilbert-valued just because that's relevant to practice. So V here can be a Hilbert space. And we're going to assume these functions have a holomorphic extension from this unit hypercube to a Bernstein polyellipse. Okay, so don't worry about the technical details here. I won't define what a Bernstein polyellipse is here. If you know anything about polynomial approximation, it's just a tensor product of one-dimensional Bernstein ellipses. But essentially, it's a region in CD that contains your hypercube. Okay. And we're going to assume that our parameters defining our ellipses satisfy this type of inequality here. Okay. And again, this is for technical reasons. This comes from the approximation theory. I won't discuss the details really very much. But let me point out here that this condition doesn't, it's unchanged by reordering your parameters here. Okay, so it's a function of the parameters, but it's not affected by how you order them. So of course, I mean, in these kind of work, you can write down any class of problems that you like and prove theorems about it. Obviously, one thing that you should ask is this a reasonable class of functions to work with? And it turns out the answer is yes. There are many parametric models, in particular parametric differential equations, for which the solution map or the function that you're interested in has this type of holomorphic dependence. Okay. So it depends on a smooth way on its parameters. Let me just point out one small thing here. We don't assume that we know what these rho j's are. Okay, so we assume that we know this gamma in order for the theoretical results. We don't assume that we know the rho j's. Think of this as not assuming we know the sort of more important directions in our parameter space. I see there's another question. So another question. Can you give us any intuition into what the inequality does beyond allowing permutation? Yeah. So basically, this is the best this will come up in the best approximation rate via polynomials and neural networks. So if you, in a special case, if you take d equals 1, this is going to reduce down to essentially log rho. And then we'll see in the next slide that the approximation error is going to depend on the exponential of n times log rho, which is like rho to the negative n. Okay, so so first of all, let's start with an existence result. Okay, so I said that there's a large literature on DNN existence theory. Let me pick out the one result or one of a number of results that's relevant for this class of problems. So this was proved a couple of years ago by Opshur, Schwab, and Zek. And what they proved is the following. So suppose you take a function from this class, then there's a ReLU DNN of a given architecture. I won't specify the architecture, but essentially the width, the depth, and the number of parameters depend mildly on S. And for this deep neural network, you achieve an error that's exponentially decaying with rate S to the 1 over D. And this is where your gamma appears. So what this says is over this class of problems, there are deep neural networks that are not actually too deep or too wide or have too many parameters that can approximate holomorphic functions with exponential accuracy. Okay, so exponential in S to the 1 over D. how this result is proven is using the sort of fairly standard approach in this kind of existence theory literature, which is to essentially take your favorite approximation scheme, which would be a polynomial scheme, and then approximate the polynomials using deep neural networks. Okay, so this is the sort of existence result. So think of this as the sort of benchmark. And then the question to ask is, well, can we train a neural network? Is there a way, can we prove that there's a way of doing training that can achieve this type of error? And this is what we were able to prove. So let me skip a number of the technical details and let me just focus on the sort of main parts. So this says there's a class of ReLU DNNs of a given depth, width, and number of trainable parameters that depends mildly on on D, your dimension, M tilde, which is effectively your number of samples, and your gamma. There's a regularization term, and there's a choice of regularization parameter. Interestingly, this is independent of your function, such that with high probability, any minimizer from your training problem, so any neural network that you get that minimizes your loss function, which is just a regularized L2 loss, from noisy samples, satisfies the following error. So the error decays like the exponential of negative gamma M tilde to the 1/2D, okay, plus your noise term here. Furthermore, you can actually do this training efficiently. So this theorem says that you can achieve with a deep neural network guarantees on accuracy. Okay, so this is the exponential term here, and sample efficiency. So this is your M here. So your error is going down like essentially the exponential of M to the 1/2D. You get stability with respect to noise, and you have some statement about computational cost as well. So in other words, we like to call this the practical DNN existence theorem. In other words, there's a provably good way of doing training. So that's the scalar case. We can also do this in the Hilbert-valued case as well. I think I'll skip this. There are some extra technical bits that we need as well. But let me just sort of discuss a couple of things related to this. So the sort of main takeaway of this is that there are provably good ways of training DNNs over this class of problems. In fact, the rates that you get are identical to the best known rates for state-of-the-art polynomial methods. Okay? So you can do at least as well as these methods. Unfortunately, that also implies a big caveat. And the big caveat is that the way this theorem is proved is by borrowing a leaf out of the existence theory book, which is just to emulate a standard technique as a DNN training problem. So we take compressed sensing based polynomial approximation and emulated it as a DNN training problem. Okay. So in other words, whilst this can do at least as well as standard methods, it's not intended to do any better. So this is not something that I would ever really consider implementing to try and outperform these methods. What it does, though, is it aims to sort of highlight that there is potential. You can at least perform as well as state-of-the-art things. And just to give you a sort of insight into what we're doing more of now, so actually we're focusing a lot more on the parametric PDE problem. And here we find by essentially empirically tuning our architectures and getting our training right and working very precisely with a number of these things using the experience that sort of we have from the past work with Nick, we're actually able to outperform these state-of-the-art methods. So I won't go into the details of these diagrams here. These are results from a parametric PDE in 30 dimensions. And we can see here we're getting better performance with the various deep neural networks with the right types of architectures. Okay, so that's the first part of the talk. And now I want to switch gears completely and talk about inverse problems. So this is, as I said, this is not going to be related to the first part of the talk in terms of the problem or the mathematics, but hopefully the sort of main thematic ideas are going to be the same. So let's talk about inverse problems now. So the general problem that we're interested in now is we have, in generality, we have two Banach spaces, X and Y. We have a mapping from X to Y. And we have some measurements, Y equals AX plus E, noisy measurements of some unknown X. And given Y, we want to recover X. So the typical example that we'll talk about is a linear discrete imaging problem. So here X is, let's say, Cn, so it's images with n pixels, complex valued images with n pixels. Y is Cm, so space of measurements. And your A here is just a matrix, which is n by n, which is a subsampled Fourier or radon transform. And so Fourier transform comes up in a number of important imaging modalities, including MRI. Radon transform, of course, comes up in any kind of tomographic imaging. So this is an important problem to solve. And one of the things that makes it challenging is that the number of samples M here is often highly limited. Right? So the amount of data that you can get from an MR scanner is often highly restricted. Okay, so it's essentially a function of the time that you spend in the scanner. So I think probably I was not able to attend Janina's talk this morning because I think it would have been about 2 a.m. for me. But I believe she talked about inverse problems in imaging, and I believe she probably talked about model-based approaches using sparse regularization. So while there's sort of been a lot of work of deep learning in the last few years for inverse problems in imaging, it's perhaps still fair to say that for the moment, the state-of-the-art methods are based on some kind of sparse regularization. So in other words, you reconstruct your image by fitting your data. Sorry, this should be a Y here, not a U, plus some penalty term here. And here, J, your penalty term, is some kind of handcrafted regularization term as the terminology people like to use. So it could be a TV penalty, so the one norm of the gradient, or it could be the one norm of the wavelet transform, or something more fancy, shearlets, curvelets, or a combination of several things. Yeah. And one of the reasons that we like this, well, first, because it works well, but second, we know under the right conditions, we have very nice theory that describes stability and accuracy for this problem. Okay? And this is through the theory of compressed sensing. Okay, so as I said, and as I think you probably heard this morning, over the last 3 to 5 years, there's sort of been an explosion, perhaps fair to say a revolution in inverse problems in imaging using deep learning. There are many, many different ways in which you can set this up and try and solve this. I won't go into any of the details of how you do it. But the general idea is what you're trying to do is you're trying to use training data. So your training data here consists of pairs of measurements. So for instance, Fourier samples, if you're in Fourier imaging, and the underlying images, so the training images. That's your training data, and you're trying to learn a deep neural network that's an approximate inverse mapping. So it's a mapping from Y to X. Okay, and so this started a few years ago and is causing has caused a big stir in image reconstruction. So there are sort of many papers now with a series of very bold claims about how effectively deep learning can perform for image reconstruction, including very bold claims such as AI transforms image reconstruction, and many claims about outperforming state-of-the-art methods beyond this. So the question that we started asking about 3 years ago was, should we be concerned by this? Okay, is there anything that could go wrong with using deep learning for inverse problems? And the answer turns out to be yes. And so I think if you were listening to Des Hines' talk earlier today, you would have heard a lot about instabilities in deep learning. And it turns out that in deep learning for inverse problems are highly susceptible to instability. Okay? These are often referred to as hallucinations in this community. So in other words, artifacts in your reconstruction that look like they may be physical, but are actually just artifacts of the trained neural network. So more generally, as well, the performance of trained neural networks for these types of problems, that they can suffer from sort of quite unpredictable generalization, as we'll see. So if you sort of want to read more about this, we have more to say on this in a paper from a year and a half ago with Anders and Vegard and Nina. Let me just sort of pull out a couple of quotes to emphasize that this is certainly an issue. So the first one comes from the results of the 2020 FAST MRI challenge. So this is an open challenge for using machine learning to solve MRI, the inverse problem in MRI. And they highlight midway through their paper on the results, they highlight hallucinations and hallucinatory features, describe them as being non-acceptable, and talk about them being especially problematic if they mimic normal structures that are either not present or actually abnormal. So that's from the FAST MRI challenge. There's another quote here from fluorescence image reconstruction. There are various other areas in which these hallucinations have been observed and raised as a serious problem for imaging. So let me just highlight a few of these things. So we started to look into these things about 3 years ago, and I think our work was essentially the first to highlight, to show that there were that deep learning approaches for inverse problems could be unstable. So here's a particular example, and what we do in this example is we take an image X and we construct small perturbations. In these cases, these are adversarial. These perturbations are visually imperceivable to the human eye. And then what we do is we run our reconstruction on the perturbed images. And as you see, these have a dramatic effect. Okay, so here's the original image. So we take measurements of these images, run the reconstruction with, in this case, we're using this automap network. And you can see it destroys the reconstruction of the image here in a quite catastrophic way. Let me point out that this is not something that we should have to put up with. If you use sparse regularization techniques and you implement them in appropriate ways, then these methods are perfectly stable towards perturbations, including adversarial perturbations. So these are actually adversarial perturbations for sparse regularization. And here, so you see they're visually imperceivable. And again, here's the reconstruction. You see very little effect here from the perturbations as indicating a stable method. There are a bunch more examples, which I think I won't go into in too much detail. So here, these are deep learning reconstructions. These are the bottom one here is for CT. The top one here is for MRI. Again, you see these types of artifacts here due to instabilities. So when we started doing this work, one of the questions that we would receive very frequently with this work is, well, you're constructing some sort of adversarial perturbation. Is this just a rare event? I mean, is the situation ever going to arise in MRI that the noise that you encounter there, or the other modeling errors or anything like that, are they actually ever going to cause some kind of adversarial perturbation that will destroy your accuracy? And to counter that, then we sort of looked at sort of more random perturbations, and we can show that for certain networks, these can be badly affected by just random noise. Okay? And theoretically, we can show that this is the case as well, as I'll discuss in a minute. So here's an example of just random noise, which can badly affect a network here. So here, essentially what you see, here's a crop of your true image. And with certain random perturbations, essentially what happens is you now get a gap appearing here where you should not get a gap. Okay, this is part of your tissue. there should not be a gap here, and that's an artifact or a hallucination created by your reconstruction. Finally, there's also unpredictable generalization. Okay, so you can make very small changes to your input image, and you can drastically change your the error in your reconstruction. So we have a couple of examples of this as well in practice. And again, let me emphasize, this is not something that existing state-of-the-art methods suffer from. They have fairly predictable generalization. So, okay, so the sort of main takeaway here is that deep learning for inverse problems in imaging can quite easily become susceptible to instabilities. Okay? So you train your deep neural network to perform some imaging task, and then it can be quite easy to come up with perturbations that will cause dramatic artifacts in your reconstruction. Okay? You can also encounter hallucinations. So you can also encounter artifacts that look like they might be physically plausible features, but actually they're just artifacts of the reconstruction as well. So after we sort of established empirically that these kind of effects could occur, we started to think about, well, what kind of mechanisms can drive deep learning to become unstable? Okay. And let me point out here, we have an article in Science News from March of this year that discusses instabilities in deep learning. We also have a paper on the archive that describes the mathematics behind some of these instabilities as well. And so there are different mechanisms that can cause instabilities and hallucinations, but one of them, and one that's perhaps the sort of one of the more fundamental, is the idea of overperformance. Okay. So overperformance is loosely the phenomenon where you have trained a deep neural network to reconstruct two images that are far apart. So X and X primed are distinct images. However, their measurements are close together. Okay. So as long as their measurements are not identical, you can always train a neural network to reconstruct these images well, regardless of how close their measurements are. But you might imagine that this is going to cause problems. Okay, so if you have measurements that are very close together and you have a mapping that's sending them to things that are very far apart, you might start to think that this is going to inevitably lead to instabilities. And this is exactly what we showed in this paper. Oh, sorry, I see there's a question in the Q&A. Okay, so a question from Stephen. Are we asking a DNN to do something that humans can't do, or are humans better at actually predicting the inverse image from samples? There's not really any, so human can't really do this because, I mean, your data is Fourier samples of an image. So unless your brain can perform a sort of inverse Fourier transform from subsamples, then you can't really have a human do this. So you need some algorithm to perform a reconstruction here. I hope that answers your question. And another question from Colin. Can you say anything about the properties of images on which deep learning exhibits instabilities where non-deep learning techniques don't? Short answer, no. I might have to think about that and get back to you. So, yeah. Okay, so here's our theoretical result explaining sort of this mechanism for obtaining instabilities. So some very mild technical conditions. So your reconstruction map, so your deep neural network here should be continuous. That's not really a problem in practice. Suppose that we have two images, X and X prime, such that the two images are not close. However, the measurements of them are close. Okay? This can easily happen in practice because we are almost always in the situation where we're taking fewer measurements than the dimension of our images. So we're always doing some kind of subsampling. So you can easily end up with distinct images that are close. Essentially, their difference should lie in the kernel of, or lie close to the kernel of your measurement operator. Thirdly, you've trained your neural network to reconstruct these images well. Okay, so this is the statement here. Then the following column. So first of all, there are instabilities. So more precisely, around your measurements of X, there's a ball such that if you look at the Lipschitz constant of your map, okay, so the Lipschitz constant is a measure of stability of your map. So it's a measure of the effect of perturbations on the output relative to the size. This is bounded by this quantity here. So essentially, if X minus X primed is order 1, this looks like 1 over eta. So the better and better you can reconstruct X, and the closer and closer their measurements are, the worse instability you're liable to get. Secondly, we also have hallucinations, and specifically we can have false positives and false negatives. So in other words, the statement here is quite general because it involves various closed balls, but at its essence here it says, suppose I take X, I take my measurements of X, and I perturb them. Okay, I can find a perturbation that's going to give the following effect. Then I feed them into my neural network, which should be phi here, but is F, so apologies for that. Then the reconstruction that I get is actually close to a different image, X plus Z, okay, where Z is a non-trivial perturbation. You can also have false negatives in the same way. Okay, so false positive is going to think about this in the following way. So think about X as a healthy brain, and you have a small perturbation here, and it gives you reconstruct your brain X here plus a little tumor. So you reconstruct an unhealthy brain. So that's where the terminology false positive is coming in here. I see there's another question. Is the better and better you can reconstruct, the worse the instability effect, something like an overfitting problem? No, I mean, so overfitting, we would more sort of classify as you do very well on your training set, but you do very badly outside your training set. So here, we're not saying that you do badly outside your training set. We're actually saying that near the images that you perform very well on, you can be very unstable. So so you don't need to overfit here. In fact, you could, the X and X prime could be elements of your training set. They might not be. They could just be two images that your network performs very well on. And this only needs to hold for two images. So you don't have to overfit on your whole training set if you want to phrase this in terms of overfitting. So it's somewhat related, but not the same as overfitting. Okay. Yeah, let me just sort of re-emphasize that these things can occur in practice. And here was a previous example. There are more examples that we have in the various papers on this as well, of these false positives and false negatives. Okay, so let's just sort of take a pause for a second. So where we're at this point, we've shown that instabilities can easily occur in deep learning for inverse problems. We've shown one of the sort of, what we think is one of the key mechanisms that drives instabilities, which is this overperformance. What this sort of leads you to naturally is realizing that there must be some trade-off between accuracy and stability. The more you try and perform very, very well with learning, the more likely you are to fall under into these conditions here, which are going to cause you to become unstable. So there's a subtle trade-off between performance and stability. And so then we started to ask the question about lower bounds. Okay? Are there actually deep neural networks that are guaranteed to be stable and accurate in an appropriate sense for inverse problems, and can these be constructed? Okay. So to prove that these exist is actually not too complicated, but can these actually be computed? So again, in order to think about this question mathematically, we have to declare a class of problems that we're going to work on. And so what we started to think about was, well, a class of problems that we're very familiar with. So class of problems that we're familiar with from the sort of compressed sensing literature, but also relevant to a bunch of applications, including MRI, is the class of the following. So first of all, your measurements are going to come from Fourier measurements. Okay? So your matrix A here is a subsample Fourier transform with a certain type of sampling. So I'm just going to use an inverse square law sampling scheme here for simplicity. You could use more complicated schemes if you like. And what we're going to think of is we're going to think of the class of images that are whose gradients are approximately sparse. Okay, so this is a model for imaging. It's not a massively sophisticated model for images, but it's a reasonable model to for real-world images. So what I formally mean by this is think of the set of measurements y equals ax plus e, where x is an image and e is noise, and such that the gradient of x, the best S-term approximation of the gradient, plus the 2 norm of the noise is bounded by some zeta here. So in other words, the smaller zeta is, the better approximated your image is, or the sparser the gradient of your image and the smaller of your noise. Okay. So one way to think about this is just to think about this is the class of problems that we know we can do well on with sparse regularization, specifically TV minimization approaches. Okay, I should say there are various other setups you consider here. You can consider orthogonal wavelets, analysis, sparsity models. There are a bunch of other things. I just picked this one for concreteness. Okay, so then what can we show? So we can show the following. So I should say that we're not the first people to try and do this. This was first done by Anders and a couple of his students, including Matt Colebrook. So we can show the following. Suppose that your number of measurements is bigger than S times a logarithmic factor. Then you can compute a deep neural network such that with high probability, every image in your class is recovered up to an error that's proportional to zeta by this deep neural network. Furthermore, this network is computationally efficient, okay, in the sense that it's actually not too deep. Why is this computationally efficient thing important? Well, one of the primary selling points of deep learning for imaging is that it can actually perform image reconstruction faster than sparse regularization techniques. And again, this is related to the depth, because the depth is going to affect how expensive a forward propagation through your network is. So again, here we have statements about accuracy and stability. This is all tied up in this bound here. We can say something about the number of samples you need, which is important for applications like MRI. And again, we can say something about computational cost. So, oh, sorry, I see there's a question in the, oh, okay, yeah. Okay, so I'm sort of rushing to a conclusion here. I won't go too much into the technical details, but say that the way in which we are doing this is to emulate, again, state-of-the-art techniques as deep neural networks. There's a lot of new stuff involved in how to do this. It's not straightforward at all, and we're also using novel optimization schemes in order to get these kind of results. I should point out that the result I presented is by me and my master's student. It's based on a paper of Anton et al. And various others, including Anders and Matt Colebrook, which looked at wavelet-based sparsity. So here we're looking at gradient sparsity. Okay, let me illustrate. So I actually taken an illustration from the paper. Let me just finally illustrate that this does work. It does give you stable reconstruction. So this is the automap reconstruction, which is very unstable. This is these stable neural networks. And here you can see very nice stability properties. Okay, so let me just rush to the conclusion. So this talk was about deep learning for scientific computing. I think there's a lot of potential here. However, there are challenges around stability, unpredictable generalization, and the gap between the mathematical existence theory and practical performance. So what we've been trying to do in this work is to examine the practical performance of deep learning through rigorous computational experiments, using the metrics that are relevant for the various problems. And then we've been trying to essentially prove lower bounds to show that we can compute deep neural networks that perform at least as well as state-of-the-art methods. Then, of course, the big ongoing problem, which I haven't addressed in this work really in any detail, is, well, how can we do better? Can we use this insight to develop deep learning methods with robust and reliable performance that outperform the current state-of-the-art techniques? So let me end there, and I'm going to end with a very shameless plug. So if you're interested at all in what I've talked about, conveniently, the two parts of this talk are related to two books which I've written. So the second part, which is a book which is out now with Anders, is on compressive imaging through CUP. The first part of the talk will be coming in early 2022 and published by SciAm. So let me end there. Thank you very much for your attention, and I'm happy to take any further questions.